I've drawn the diagram partly already because it was too hard to make things line up piece by piece, but we'll label them in the order that you would construct them. So, proposition 9. If a cone is cut by a plane which meets both sides of the axial triangle and is neither parallel to the base nor situated subcontrary-wise, then the section will not be a circle. So, we're going to have a cone and we're going to have a plane, and the plane is going to meet both sides of the axial triangle, and we're going to imagine that it is a circle because this is going to be a reductio ad absurdum. If you're not familiar with reductio ad absurdum, what it means is that if there are only two cases, something either is something or it's not something, instead of proving that it is a certain way, you can assume that it is the opposite way and then prove that that case would be impossible for some reason, meaning that the only remaining way is the way that it is. So in this case, we're trying to prove that this is not a circle, and we're going to start out by assuming that it is a circle, and we're going to see that a circle constructed not subcontrary-wise will turn out to be subcontrary-wise. We're going to learn that basically the only two cases in which this would be a circle is if it's parallel or subcontrary-wise, and if it's not either of those two things, then it can't be a circle. Okay, so we have this cutting plane, and we have this base. Since the cutting plane is not parallel to the base, that means that it'll meet the base if it's extended in some direction. So we're going to extend this plane in this direction, and we're going to create the line FG. We'll put the point G later. And this line is going to represent the where those two planes coincide. The common section. Yeah, the line which is the common section of the two planes. That's how to say it. Next, we're going to find the center of this circle. We're going to label it H. We're going to connect H to this line at the point in which those two lines are perpendicular to one another. Then I'll label this point G. Then we're going to draw GH this way and extend it so that it's a diameter of this circle. I'm going to label this B. We're going to label this C. So this is how we're going to create our axial triangle. BC is going to be the diameter, and AB and AC are going to be our sides of the axial triangle. Next, we're going to take this point G, and we're going to think about it in respect to the plane of the axial triangle, which is now ABC. It's in that plane, and we're going to think about the plane of the cutting section here, and the cutting section connects to this line FG. So that means that this line G something something is in the common section of the two planes, the one being the plane of the supposed circle and the other being the plane of the axial triangle. So that would mean that this is a straight line. So we're going to now label this D and this E. Okay, so now we have our supposed circle, we have the line DG, and now we're going to pick some random point K, and we are going to draw a line KL through the section. We're going to draw KL so that it's perpendicular to the plane of the axial triangle ABC. And you'll remember that this makes DE the diameter, and it'll make KL bisected at this point M. But anyway, this is now parallel to the line FG, because FG was already constructed so that it's perpendicular to the axial triangle. And since FG is in the plane of the base, BC, it's also parallel to the plane of the base. Now let's draw another line through M. And let's label it NX. And let's construct it so that NX is parallel to the line BC. So we've got this line parallel to the base, and we've got LK parallel to the base. So all of these points, L and KX, could represent points in a plane which is parallel to the base, and therefore the section of it would be a circle. So let's draw a circle around those points. Okay, so K and M, this line KML, is common to both circles, supposed circles. On one hand we have the circle LDKE, which was our cutting plane at the start, and on the other hand we have LNKX, which was what we just constructed. And since both of those are circles, they have the property that the rectangle made of the parts of the diameter cut off by something perpendicular to it is equal to the square on the side cutting the diameter. So if we were to write that out, let's pick a different color. We would get that on this circle, the rectangle DMME is equal to the square on KM. DMME, KM. On this circle, the rectangle NMMX is equal to the square on KM. NMMX, KM. So you'll notice that the square on KM is in both of those equalities. So you can substitute. You can get that NMMX is equal to DMME. So let's go over means and extremes again. So means and extremes is if you have any ratio x, y, z, a, the rectangle made up of the things on the extremes is equal to the rectangle made up of the things on the means, meaning the things in the middle. So if you have a rectangle equal to another rectangle, you can do this process in reverse. So on one rectangle, you put on the outside, and on one rectangle you put these terms on the inside, and you get this ratio. So that's what we're going to do with this rectangle equality. So NM and MX are going to go on the extremes. DMME are going to go on the means. And we're going to get this ratio. Now let's take a look at where those lines are in this diagram. So you've got NM, DM, and you've got ME, MX. So if you were to complete these triangles, we know that in similar triangles you can set up a ratio with the sides that correspond, meaning the sides that sit across of equal angles in their respective triangles. So DMMN represents one similar triangle here, and MEMX represents another similar triangle here. So let's think about the sides that they sit opposite of. Well, DM sits opposite this, and that corresponds to MX. MX in this triangle sits opposite this. So that must mean that D and M is equal to the angle XEM. Okay, so now let's think about these circles again. So on one hand you have this constructed circle, which we constructed parallel to the base BC. I'm going to get yet another color. How about blue? And let's think about the triangles that it makes with the axial triangle. Let's draw this a little bit better, because what we're trying to do is show that DN, this line here, is supposed to be the same as this blue line, but I haven't drawn this very well. So since this line NX was constructed parallel to the line BC, it's going to make this angle here equal to this angle here. Now we've just shown that this angle is equal to this angle. So let's draw out this triangle, and this triangle is made with the cutting plane this time, which we have assumed is a circle, and we have assumed that it is not subcontrary-wise. So in this triangle you can see that this angle would be equal to what we just proved this angle is equal to this angle. So that means that this angle is also equal to this angle. Now these must be similar triangles, because this angle is shared at the top, and every triangle, the angles in it are equal to 2 right angles, so that would make these remaining angles equal. So what we're learning is that this is situated subcontrary-wise, because what it means to be situated subcontrary-wise is that they're similar triangles in which the angles which are equal are sort of flip-flopped. So we had constructed this circle assuming that it's not subcontrary-wise, but we find out that if it is a circle, the only way it can exist as a circle is if it was situated subcontrary-wise. So this means that if it was not situated subcontrary-wise, it would not be a circle. So if a cone meets both sides of the axial triangle, if a plane cutting through a cone meets both sides of the axial triangle, the section that it makes is not a circle unless it's parallel to the base or situated subcontrary-wise. So that's QED.